All right. So has somebody invented message passing in the break? The question is, how can we map what we've just seen with Dijkstra's algorithm, shortest path, and so on? How can we map it to our maximum a posteriori problem?
We can also draw this kind of picture that we had there, and in the horizontal line are the different classes we have, and in the like in the rows are the 1, 2, 3. So we have 3 rows and 3 columns, and then a link between 2 nodes, which would be the cost function we have in the potential.
Yeah, perfect. Good. Let's do this. Okay, just to be super explicit. We're now taking we're taking this and we're taking that and we're putting it in a single picture. Yeah. So we start with 3 nodes that represent the 3 possible states for the first random variable, and we have a source node which is connected by 0 cost edges to all of these. And now this will get, maybe you want to do this a bit bigger than I did. Okay, now we need to encode this working of our first pairwise factor. So what number do I, so this is for variable z2, excuse me, z2. What cost do I associate with this vector here? The inventor of the algorithm or anyone else? This is 2. Why? Because a transition from A to A, class A to class A costs 2. Okay. What number do I put here? 4. Because a transition from A to B costs 4. What number do I put there? 7. Because according to my matrix, an A to C transition costs 7. Great. Okay. What cost do I put here? Yeah, I was illegible, but 104. Yeah. So 104, and this one has a cost of 5, and this one has a cost of 5 after your correction, and this one has a cost of 104, and that one has a cost of 105, and this one has a cost of 4. Okay, so now we can compute the different costs of reaching this node here. The possible costs of reaching the first node are 2, 104, and 104. The possible costs of reaching the second node are 4, 5, and 105. And for the third node, it is 7, 5, and 4. Okay, now we want to find the cheapest path to any node. So we find the minimum for each of them. So this is the cheapest way of reaching the first node. This is the cheapest way of reaching the second node. And that is the cheapest way of reaching the third node. So if I wanted to draw these paths, I could do this. So let's say this would be the blue path. This would be the green path. And this would be the red path. Okay? Good. So now I have reached the possible states for random variable 2, and I am actually selecting the minimum out of these. Yeah, so I'm taking the minimum out of these three numbers, and the minimum out of those three numbers, and the minimum out of those three numbers, and then I get 2, 4, and 4 respectively. So these are now the minimal costs of reaching a given node. These are the minimal costs of reaching the respective nodes. And a respective node means the respective label for random variable z2 in this case. And now it goes on. We'll do this one explicitly also. So what's the cost associated with this edge? Two, because now we're looking at this potential here, and the cost of transitioning from A to A was 2. This cost is 3, because we have a 3 here, and this cost is 6. This cost is 102. This cost is 2. This cost is also 2. And this cost is 102, 102, and 1. Okay, so now to reach this node here, I can either start from a cost of 2, and then I traverse a path of cost 2, which gives me cost of 4. Or I can start with a cost of 4 and add a cost of 102, which gives me 106. Or I can start with a cost of 4 and add a cost of 102, which also gives me 106. Similarly, for the second node, I can start with 2 and add a cost of 3, which makes 5. Or I can start with a cost of 4 and add 2, which makes 6. Or start with 4, add 102, gives 106. And finally here, I have 8, or I have 6, or I have 5. Again, I take the minimum because I care about the cheapest path to any of these nodes, and the results of taking these minima are 4, 5, and 5. And so the overall shortest path from source to target, because I can now add my target node down here and connect it with edges of weight 0. So the overall cost is 4. So this is the overall cost of the shortest or the cheapest path. And that, because we have represented an energy function, now is the overall lowest energy that we can achieve for our small Markov random field, for this small chain-shaped Markov random field. So what we have just done is we have computed the minimum of the energy, which was a function of Z1, Z2, and Z3. We have optimized it over all variables, and we found that the value of this minimum is 4. Now that's very good, but it does not give us the argmin. It does not give us the labels that result in this lowest energy. So, do you have a suggestion on how to recover now the optimum labels?
Well, the path the computer tells us which labels we should choose.
Yep.
If we just trace it back, we know that the values.
Exactly, the path tells us. And now let's figure out this path. Yeah? So here, and then, where does the path continue from there?
Because that's just a cost, right? The node is
Yeah, fine. But where does this come from? Or how did we get there?
Maybe we can just use the stack. We pop into the stack. And then every time we find the minimum for each layer, then we pop into the stack, and after that we can pop out.
So what you're saying is we could have remembered on the forward path what was the cheapest path, but now we haven't remembered. Yeah, we forgot to do it, and now we still want to recover it. So how can I recover it?
I have to check going which way I will have a cost difference, cost of 4. So I know one path takes 2, and the node it leads to has already a cost of 2.
No, yeah, okay, fine. Or, that's correct what you're saying, or I can just look at the minimum. If I remembered that, if I did store it, then I could see, okay, the first argument of the min did give me the min. But if I didn't store it, then I have to do what you told me. Yeah, I look at which of the predecessors. Yeah? In this case, this one. Okay, and from there, same. Okay. So, tac. So this is the minimum path, and now I find that the optimum labels were actually A, and A. Yeah, because my minimum path always went down the left-hand side. So we find the optimal configuration, or the argmin, so we find the optimal configuration Z star, which is given by the argmin over Z of my energy function by an operation that you have just invented, which is called backtracking. Okay, now let's compare this. Is this any surprise? Let's look again at the unary factors. If we go back here, just looking at the unaries, I would have selected class C at the third node, either class A or class C at the second node, and class A at the first node. But now, using the pairwise interactions, we find that the globally optimal solution is actually AAA. Yeah? Because we look at both the unary and the pairwise potentials in determining our global optimum. Questions? Okay, then now this was all by means of example. Now I want to say this a bit more abstractly. So let's say for what have we been doing effectively? Yeah? We looked at a chain where we had Z1 coupled to Z2 coupled to, and so on, up to some variable Zn. And we were interested in recovering the minimum over all Z of our energy of Z. And the energy here, if I have only the pairwise terms, is given by the sum of Ci I plus 1 of variables Zi and Zi plus 1. And just to write it down explicitly, yeah, so we have Ci of n minus 1 and n plus, and so on, plus psi of Z3, Z2. The other way around, huh? Excuse me, 2, 3. Plus the potential 1, 2. And we want to minimize over all of these. And now when we perform this minimization, we see that if we want to minimize over Z1, for example, all of these terms here, excuse me, these terms here are independent of Z1. So that means I can pull in my minimization operator. I can say the minimum over Z1, I find it just over this term here. Okay, and up here I have my minimum over Zn of my first term. Yeah?
Don't we need some more brackets?
Yes, thank you. Check, 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 check. Okay, thank you. Okay, and now if we look at it abstractly, this psi 1, 2 is a function of variables 1 and 2, but I minimize over just Z1. So effectively, I get a function which depends on Z2. So I get a function which I'm calling m here of Z2. And here I get a function of Z3, and I'm also using indices of these functions to say that this is a message from 1 to 2, this is a message from 2 to 3, and so on. so I solve my minimization problems one by one, and this is exactly what we also did up here in our computational graph. Yeah, we first solved these minimization problems, and then conditional on these answers. So what went from here to there can be seen as a message from 1 to 2. It's a vector. And this was the minimization over Z1. And then here at this stage, we did a minimization over Z2. And we sent a message from 2 to 3, and so on. Okay, so what we did up there in the computational graph is now written up here in terms of an optimization problem. And importantly, this here is an exact equality. Yeah? So there was no approximation made. It's just that we applied a minimization, or we did perform a minimization over only those summands which depended on a particular variable. So we solved the problem piece by piece in a forward fashion. So let's say on a chain, we can solve a joint minimization problem as a sequence of optimization problems. And this makes for huge savings, of course, because if we look at this joint optimization up here, this one, the search space here, if I did a brute force search here, it would be 3 states, or let's say k states per variable, and then we have n variable. It would be k to the power of n. And here, through this sequence of optimization problems, each of the optimization problems itself is only of cost k, because we investigate k different classes, and then we have n iterations of this. So this is n times k versus k to the power of n. So gigantic savings, okay? Thanks to dynamic programming, so thanks to the reuse of computations. Any questions? Yeah?
What would be an abstract definition of dynamic programming?
What is an abstract definition of dynamic
An
programming?
example of dynamic programming, what does term dynamic programming in general means?
Dynamic programming in general means that we identify and solve the overlapping sub-problems and then exploit optimal substructure to compute the overall solution from solutions to the sub-problems. Now, in practice, in principle, there are 2 ways. When I have a problem, either I could verify that it has overlapping sub-problems and optimal substructure, or I could try and invent a dynamic programming algorithm and then prove that it solves the problem. I think usually people do the second.
The optimal substructure here is important to prove unique, or that you have 1v1 solution So the solution is unique and you can backtrack it
Yes.
Without.
Yeah. So, you know, the solution in this problem need not be unique. So there can be two configurations which have the same energy. And then by backtracking, we just randomly pick one of the two.
It means using the dynamic programming, we can avoid the redundant cases.
Yes, we can avoid redundant computation. Mm-hmm. Okay, so we started with a discrete number example, with a concrete number example. Then we went to the chain, and now I want to go to the next higher level of abstraction. I will give you now the algorithm. I will now just pretend that the same works not just on chains, but it also works on trees. And I will not prove it now. So the only difference is that in trees, we have sometimes different messages from different branches coming together. So I'm giving you one example here. So I'm making up so the headline here would now be message passing min sum message passing, or this is also called belief propagation. For arbitrary, excuse me, it's all the fault of the digitizer, you know. For arbitrary tree-structured discrete graphical models, I am making up some tree-structured graphical model here. Let's say that does the job. Then the procedure works as follows. And if you want to read up on this, you can do this, for example, in the book by Prince, of which I've been showing you the cover in the first hour. So I'm now giving you the recipe, which says first pick an arbitrary root node. It need not be a leaf. You know, it can be any random variable. I am now picking this one. Yeah? I'm calling this one root. Now I'm ordering all other nodes by their distance from the root. Let's say, so this is a distance of 1, distance of 2, distance of 3, distance of 4, distance of 5.
Excuse me, in this case, is the higher order pairwise?
This is now a third order factor that you see here. Yeah? So pairwise would mean that the factor is connected to 2 nodes, and here I've connected it to 3 nodes. And this is now the only part here which makes this thing different from a chain. Yeah? If it wasn't for this factor, it would be a chain, but thanks to this factor, it would be a chain with unary potentials, but now it's a proper tree.
And tree structure means?
No loops, a graph with no loops. If you like, you know, I can add another one here. So a tree is a graph with no loops, okay? So we pick an arbitrary root node, and then we send messages from the leaves. So leaves are, local maxima of distance, if you like. So the leaves in this case, if I give them a blue color, this would be a leaf. This would be a leaf. Actually, let me delete this one here. This would be a leaf. This one would be a leaf. Okay. And the messages look like this. So we can have factors as leaves. Then we send a message from a factor psi s to a random variable zs. So a factor can only be a leaf if it is connected to a single random variable. And this message depends on the state zs. So, if I could try and make a distinction and write a capital Z here to say this is a random variable, and now write a small z to say that this is a particular realization, but I'm not making this distinction here in the following, because anyway, you cannot, I myself, when I read my handwriting, I don't know what's big and small. Yeah, so I'm just writing z here, and this message is just what the factor itself thinks about the possible states that this random variable could be in. So this thing is a vector. For example, up here, if we say this factor is a leaf, the message it would send would be the vector 1, 3, 3 to express what this factor thinks about this random variable being in the respective states, A, B, and C. Okay, so this is a vector that is being sent out here. Now, if on the other hand, my random variable, if on the other hand my leaf is a random variable, then I'm sending a message here from a random variable zs to a factor psi t. Okay, sorry, the indices here should be different. Wait, hold on. If it is a leaf, then it's okay to write S here. But down there, I need different indices. Yeah? So now I have a message from a random variable, which can be a leaf, to a factor. And this message is just a vector of zeros. Yeah? So the random variable itself has no opinion about what state it should be in if it doesn't have a unary potential connected to it, if it doesn't have a unary factor connected to it. Okay, and now all the leaves have started sending messages. Yeah, so in this case, we've sent out 3 messages. One of them was a trivial message of just zeros. The other 2 messages were actually, vectors with numbers. And now we send messages asynchronously. So let's say this was the first generation message, 1, 1, 1. Or I could maybe do this on the arrows. This would be message 1, and message 1. Now, a node needs all inputs except 1 before it can send a further message. So the next message which I can send out now would be this one here. This would be message 2, and then comes message 3, and then I can send message 4 and message 5. And I have not given you the rules for these messages yet, but I will do it now. Yeah. So I just wanted to explain what I mean by the following sentence. Yeah. So now we send messages asynchronously. In the order in which their arguments can be evaluated. Okay, and we have two kinds of messages. One is a message from a factor S to a random variable t. And that is a minimization over the following. Okay, look, this will take too much time for me to copy down, so I will paste it into the handwritten notes. I have it somewhere here. Okay. Let's stare at this for a moment. Because I want to tell you something else before we're finished with this hour. So what we're sending, we're taking a sum over the incoming messages, and let me explain you the notation. So we are currently looking at factor S. So we're looking at all the messages that were sent to this factor S, namely from all adjacent random variables G. So these are all G's in the neighborhood of my factor S, except the random variable that we're trying to send a message to. Yeah, so we take input from all adjacent random variables except the one that we're sending a message to. Then we are adding to this the potential, or what the factor itself thinks about the message, about the random variable that we're sending to being in a particular state. And we now take a summation of these two and minimize over all of these. Yeah, so we take the incoming messages, we listen to what the factor itself needs to say, and then we minimize over all the random variables associated with this factor, except the one that we're sending a message to. So let's compare this to what we had up here. You recognize the minimum operation. Look at this thing here. Yeah. So this was the incoming message. We have added to this incoming message what the potential itself thinks. And now we're taking the minimum over the two, and this will be our new message. So what we have, what I've just shown you here with the circles, is a special case of the formula down here. It's special because previously in this chain example, we only had always one incoming message. And now, at factors like this one here, at this higher order factor, we can have several incoming messages that we need to take into account simultaneously. But the minimization is the same. Yeah? So the minimization is the same as the ones that I wrote up here, or the minimization is the same that we did in this computational graph when we were looking at these minima here. Okay? So this is the rule how to compose messages from factors to variables. And then we can also send messages from variables to factors, which is just a sum of the incoming messages except to the variable that we're sending to. Again, in the chain example, this was trivial because we had just one incoming message, so there was no summation to be done. We just forwarded this single message. And this is the generalization to trees. And the notation here is general but a bit cumbersome. And to get a better, grip on this, we will let you do this for a tiny example yourself in the exercises. Yes.
Here, we want to send a message from the leaf to the
root.
And here the S is different from ZT or.
Yes. So we start sending messages from the leaves in the direction of the root, and some nodes need to wait until they have all possible input. Yeah, so this node, for example, after the first iteration, it cannot send a message yet because it still needs input from this side before it can compute its output and send it onwards. So we always need all inputs except one. And to this one where we didn't get input, this is where we're sending our own message to.
And in the step 2, the second equilibrium is equals to 0. And it means we are forbidden to this direction transformation.
So this case 2, it's just a special case of what we have down there. Yeah. So let's say this one here is a special case of this. So there were no incoming messages, so we take a sum over nothing, and that's 0. And similarly up here, when a factor is a leaf, then it does not get any input, so this sum is 0, and all that it sends out is its own opinion about the state that the random variable can be in. So these are just the corner cases here for the leaves. Yes?
What is it called, the repropagation?
It is called belief propagation because each factor and each node propagates so here we are in the energy picture, but we can also do this in the probability space. And then each node propagates to the best of its knowledge what it knows so far about the one that it sends a message to being in some state or some other. Yeah, so here we've been sending energies, and if we don't take the logarithm, then we can send probabilities. And then it's not, then we don't take a minimum over summations, but then we send a maximum over products. So it's the identical algorithm, just in the exponentiated space. So min sum or max product, it's the same algorithm. And it was called belief propagation, I believe, by Pearl, who invented this. Okay. More questions? Okay. Okay, so we have a rule. So I think I've been pretty thorough in how to do this for a chain structured model. Yeah? Then I've given you the formula about what is going on in the chain case. And then I've taken a small leap of faith and said, you know, believe me, it's possible to do this dynamic programming also on trees. And the rule for how to do it is this one here. Okay, and it's really just a small generalization from the chains to the trees that I've not discussed in tiny detail.
And for the trees, do you have any limits, like holding for the binary tree or arbitrary tree?
Arbitrary tree, so any graph that has no loops.
And if we want to solve some comfort problem like in the image, should we at first transform the
Excellent question. So this is all very well, but now how to apply this on our original problem? Yeah. So in other words, but what if our graphical model is not tree-shaped? And here we have three options. One is we turn the graphical model into a tree. Of course, this tree will have disadvantages, yeah? With fat nodes. This is not a technical term. Technical term would be a tree of large tree width. Okay, that's the more politically correct. So into a tree of large tree width. What do I mean by this? I'm giving you here a model which is almost a tree. So let's say like this. Huh? This is almost a chain, except we have a small loop in there. So what we can always do is to say, look, I am just turning this into a big factor. But I would prefer, no, I don't like this. Let me do this differently, please. Okay, let's do it like that. And say, I turn this into a single random variable. And then I have again a tree, but this random variable will live in a higher dimensional space. Yeah? So this is a random variable which lives on a product space of its constituent random variables. And so that means some of these minimizations will need to run over a much higher dimensional space and will become much more expensive. And this is an important algorithm, and it is called the junction tree algorithm. Now, here it works fine because it's almost a chain. But what if our MRF, is really a lattice? Then, yes, I can turn it into a chain, let's say into a single vertical chain, but the nodes will be extremely, no, not even true. Huh? I can collapse it into a tree with a single unit. Yeah, but that, single unit will be as complicated as the original MRF. Yeah? So this trick only makes sense if the original graphical model is nearly a tree, but not quite. Okay, but this is exact. Secondly, if I don't insist on being exact, I can invent missing messages and iterate. Yeah, so for example here, let's say this one here is the root. I can start sending messages da, 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 da. And at this point, and this one I can also send. And now I'm stuck because this guy cannot send any further messages because it's missing one input. And this guy can also not send any further messages because it's also missing an input. Yeah? So what do? Well, let's say we simply tuck, tuck, tuck. We simply Deus ex machina, we invent this message here. We invent this message here. Now I can send this one and this one and this one and that one and that one. And then I'm sending messages back from here. And now perhaps, I'm sending an updated message this way. And I continue until the system converges or I lose patience. And this is not an exact algorithm anymore. This is an approximate algorithm, which is called Loopy belief propagation. And it's not a bad algorithm. Okay. And there is a third option. And we're almost out of time. Can you donate me 10 minutes? Exceptionally? Okay, cool. Because I never get to the third part, and that's the that's the fun. Okay, the third part. I can do dual decomposition. And I will only sketch this now. So let's look at our original MRF. I'm going to use a tiny one here. Let's just say 9 nodes. It's not getting prettier when I'm hectic. Okay. And we also need the unary factors. Okay. Good. And I can now decompose this energy function into 2 terms. Yeah, I can say this is exactly equivalent to the following. One model, let's say, this one here. Plus, and then we need another model, and they will, let me see, how can I minimize overlap? I want this one. And okay, I'm just going to build 2 comms here. even though I have some overlap. Okay, and then all the unaries. Okay. Now, there are some potentials which I've used twice, so I need to partition them. Yeah, for example, all the unaries appear twice, so I'm going to multiply them by 1/2 so that I don't overcount them. But yes. Okay. So I multiply all unary potentials by 1/2. I'm not drawing this everywhere. These potentials here only appear on the left-hand side, so I don't need to reweight them by anything. But these potentials here on the top row, they also appear in both models, so I'm multiplying them by 1/2. And similarly, these here appear in both models, so I'm multiplying them by 1/2. Okay? And now let me say so I've decomposed my model into two tree-shaped models. So my hammer works on either of the models on the right-hand side, but of course I need to couple the solutions. So I can proceed as follows. I can say the minimum over my energy, which is defined over all variables z and all potentials psi. I can write an equivalent minimization problem where I now say this is I use one copy of the variables which I call, let's say this is the horizontal, this is the vertical model, z horizontal, with a set of potentials psi h plus an energy of z vertical with potentials psi vertical. The minimization goes over both zh and zv. And now I need to satisfy two constraints. One is that my original potentials decompose, so psi equals psi h plus psi v, and moreover the solution zh that I find must be identical to the solution zv. So far these problems are perfectly equivalent. Okay?
Two cases can keep the consistency.
Say again?
I mean the first part plus the first tree plus the second tree are the solution the same. Like
Only if I require that the solutions be identical, and that's of course the tricky part. Yeah, but this is now a condition I can relax. I can say, what about minimizing? By the way, I can say this is exactly equivalent to minimizing over zh only the first part, plus minimizing only over the second variables, the second contribution, such that this is still exactly equivalent. And now I can make an approximation. Yeah? So now I say, okay, let me write this or copy this in detail here. So, and now I'm using the same thing, but I am omitting the condition that the two solutions found must be identical. So this crucial condition here I'm now omitting. And what can you say about the value of the minimum that I find? Will it be bigger or smaller or the same or what?
Small.
The new minimum that I find will be smaller because I've relaxed one constraint. Yeah? So I can, by introducing one more constraint, my minimum can only go up, not down. Okay, but now, you know, here I have a tree-shaped graphical model, and there I have a tree-shaped graphical model, and they're independent, so I can just solve them exactly by message passing, as we have just seen. But now, you know, I've omitted this condition, and I want to make up for some of this. And this is why I am now maximizing this entire thing. So maximize all of this over my decomposition, over psi h and psi v. Yeah, because I am free in how I distribute my potentials between the submodels as long as they always add up to the global model. And this will make my lower bound as tight as possible. Okay, so what does it mean in practice? I first decompose my loopy graphical model into tree-shaped models. I solve them exactly. And then I start shifting around potential between my two submodels so as to make this minimum become higher. And that is possible by means of so-called subgradient methods. And I can iterate this process until I converge. And at this point, either the two solutions will coincide, and then I know I have the exact solution to the original problem, or they will not coincide, and then I have an approximate solution. And this entire thing is called, is one example of dual decomposition. And if we decompose it into trees particularly, then we get out a method called tree reweighted belief propagation, which again is an approximate method. Okay, 11-minute overtime. I give you the one-sentence summary of today. The one-sentence summary is that message passing or belief propagation gives you exact inference on arbitrary tree-shaped discrete probabilistic graphical models in linear time, in time that's linear in the model size. This is very cool, and one of the most efficient algorithms that we have in computer vision. And this is why it's used as a subroutine even in models which are not tree-shaped, either in terms of the junction tree algorithm, or in terms of loopy belief propagation, or in terms of dual decomposition.